our next speaker from our friends from Eclipsium. So, introduce our next speaker. He is Alex. He's one of the this is foremost authorities in the fields of firmware security, and he'll be talking about AI in hardware. So, let's give it a round of applause for Alex B.
Hello. Hello. Thank you very much. That's the first time Clicker work on Linux, so that's kind of impressive. So I'm Alex. Because it's a speed talk, I will not spend too much time what I was doing in my work or last 20 years. But I like to learn devices and how does devices work and what is inside each device and how much risk that device has. And I started learning laptops and servers back in late days. And last couple of years, we learned a lot about like networking devices. That was my last year presentation. But the last also year, from like September to September, we kind of got very interested into AI hardware. And AI hardware has a lot of special things and a lot of common things with other hardware. And that will be this talk about like how does the new AI stack works. So when everyone is telling you that, oh, that's AI workload with the model and application and everything, it's actually running on the hardware, which makes that AI very performant, very, very, very fast. But that speed comes with complexity, comes with security risks. So that's what we will talk about. You will not hear any prompt injection type of stuff. You can hear millions of them during other conferences. But you will hear about like NVIDIA and Grok and other things which is related to how does the hardware in data centers performs. So, and basically, when we're talking about AI, just let's make sure that we kind of on the same page. So previously, we have software and hardware. When software using the hardware instructions in order to just executes. And then was general purpose compute. So that's like x86, ARM, and other systems. And in that stack, you kind of can see software vulnerabilities, which may be exploiting some hardware weaknesses or somewhat combine it. When AI arrived to this world, it basically kind of a third player in a town. So you have software, you have hardware, and you have now AI, which is basically a combination of software, hardware. It also has something which is called model, which is like a black box table of numbers, which no one knows what is inside, but everyone excited how does it work. And if you wanted to know about more of these, definitely recommend you to follow Anthropic. They're doing quite great research on that area. So then we have this third player on the town, and he reshaping software and hardware because he basically changed the way it's all work. And when I said hardware, what I really mean? I mean server, which has a bunch of components, including storage, compute, memory, networking, and that's needed to run training, to run inference, to run tuning. And all of these components is basically represents a new layer of complexity. And with the AI floor, it's actually almost we got a renaissance of the hardware these days. When we got companies like Grok and Sambanova and Celebras and many, many others. I'm a big fan of hardware, and I'm super excited to see last couple years how many startups building new hardware. So and when it comes to the build new hardware or build like complex hardware, again, as I said, it comes with complexity and risks and vulnerabilities. And basically, there's many, many examples of vulnerabilities within the new stack. The interestingly that it's exactly the same vulnerability we found previously. For example, Rowhammer, very interesting vulnerabilities in a memory, in a DRAM memory, when you can flip the bits in order to exploit software. We thought that we fixed this vulnerability in DDR4 and definitely DDR5. But in GPU stack, in GPU memory, that vulnerability is still present, still was present. And we basically seen also that attacker using some of that vulnerabilities to exploit and take advantage like that one, the cyber criminal groups, which is using the GPU as the way to hide the malware. And when we actually looking for every single vendor and we're thinking about, okay, what kind of vulnerabilities this vendor has, we're reading advisories. It's like fundamental skills of the security researchers is from advisories to move to the practical knowledge about the vulnerability these advisories explain, which is basically patch defense and reverse engineering and all sorts of other skills. Anyway, reading advisories is important. When you read NVIDIA advisories, you'll find UEFI and BMC type of vulnerabilities, which is affecting that components. So what it tells us? It tells us that NVIDIA stack reusing a bunch of traditional x86 stack components, x86 paradigms or ARM paradigms, which is kind of represents the way you may wanted to think about the attack surface and threat modeling of these devices. So when we basically move it a little bit from more generic explanation to more specific, we try to categorize hardware by kind of different way of this hardware work. And this is a simplistic way to think about the hardware is from the left to the right, or from the right to the left, depends how you see. But Intel and AMD system is basically general purpose compute, very complex instruction set, a lot of security features like ring privileges, virtualization, SGX, like authenticated pointer, CTE, and so on, exploit prevention technology, super complex. Like a spec of this architecture is 5,000 pages, and it's actually a small portion of really how does it work. Then you have a little bit more special compute, like GPU. GPU is like not, you cannot run anything on GPU, but you can run some flow. You can run graphics, crypto, AI, and so on. And you have a special compute. Special compute, which is basically like things which is designed to do one job, but very good. They also sometimes call it ASIC implementation. It's like the way you implement hardware for specific task. If you look inside of this chip, you kind of said, okay, I wanted to understand how does the chip behave or what is inside of this chip. You can see in this Intel picture, there is a big red box. It actually represents the management functionality of the chip. When the red box and orangey box is the compute part. When the orange box is GPU compute and the red box is CPU compute. So when you're performing the instructions, the job, this job done in one of these units. So you see, there's almost a third of the chip it's spent on management. In reality, it's actually not accurate. It's more than that because there's some things on these boxes also use it to do management. Because that's just a general purpose compute, super complex management piece, and there is some compute pieces there. When you look on a GPU one, you will see there's a less of the management piece. So management is somewhere here, but you see 4 boxes. Each of them has 9 kind of sub boxes. That's where the compute comes. That is how the GPU doing the compute. And you see it's already much more simpler. It's much more simpler than that. It has less of the management and more space dedicated to compute. When you're doing this, you also decrease in complexity, and maybe you decrease in the risks, or maybe you change in how the risk will be implemented within the device. And then you get AI accelerators like Groq, Sambanova, and Celebras. That type of the devices, you can see they have lines. And this line is actually kind of more like a stack level view when each line doing its own parallel job, which doesn't depend on other lines. And that's very elegant architecture. It's allowed to scale linearly the compute, and it's allowed to scale the parallel job. So in this chip, you have only 3% of the chip to spend to management. So in this one, you have almost 40, 35, 40. In that one, you have 3. This actually changed the architecture, changed attack surface. It changed the way actually the hardware work in general. If we'll go a little bit deeper and we'll think, okay, how that will work. So you still have management level. All of this like nice, great stuff about UEFI, BMC, network card, memory, it's all there. And it's all part of the attack surface, and there's CVEs, vulnerabilities. You can do all sorts of stuff. You have core compute, which is basically, in case of the GPU, it's quite big, powerful thing, which is running special compute, which has microcode, has firmware, and so on. Then you have software layer, and then you have hardware layer. The hardware complexity is different between the normal CPU, GPU, and the ASIC implementation. For the CPU, you heard something which is out of order execution, when you can run instruction not sequentially, but in parallel. You may heard about speculative execution, which is basically lets you to execute instruction before really time comes for that instruction, sort of speculatively. And then in GPU, you have a lot of similar concepts, but it's already simplified one. In TPU and ASICs, that architecture changed completely. You don't have caching, you don't have speculative execution, you don't have out of order, you don't have nothing of this. It makes very, very simple hardware to do very specific. So I always tell my mom this is good for digestion. So then she would kind of was not angry when I'm doing this. Anyway, coming back a little bit for the hardware back. So when you have a CPU, very complex, general purpose compute, thousands instructions, a lot of things which can go wrong. GPU, a little bit less things which can go wrong. In the GPU side, management still is there, so management still can go wrong. And then you get the CPU piece, which is ASIC accelerators, which is super, super simplified. That basically where software fully controlling hardware. So when you compromise software in the x86 and GPU, that's not the end of the game, because when you compromise software, you still need to take advantage of hardware in order to kind of bypass all of the protections like exploit prevention and like persistency protection, so on. When we're talking about CPU, as long as you get access to software, that's game over, because that software completely controlling hardware. And if the hardware is powerful enough to implement completely Turing-complete operations and persistency, then from software you can jump directly to accelerator and then stay there for as long as you need, or before the reboot happen. Depends what kind of attack you implement. So very interesting concept. Definitely recommend everyone to study. Was very new for me. If I would simplify how does that concept works in a more detailed way, if you're familiar with the GPU concepts and bitstream, that's very similar idea when it stopped working, but that's okay. Not a big deal. So when you have GPU, you have a bitstream, and that bitstream is not signed, and it dictates hardware how to work. The TPU, like Groq, Sambanova, and others, implement exactly the same concept, but in a real ASIC hardware implementation to do it very fast. So very, very genius and nice approach, changing the architecture, changing the attack surface on the hardware. So we will go a little bit deeper for the next 10 minutes, which is basically we'll cover NVIDIA and Groq in a one step deeper view, which would let us understand how complex this hardware is. And we will not focus on x86 and Intel. The reason is that there is a bunch of research even done by us in this topic, but the GPU one and the ASIC, AI ASICs one, it's a pretty new one. So that's where we will talk the rest of the 10 minutes of the time. So NVIDIA released a GB200. That's like state of the art of the hardware for 2025. Next year will be GB300, and then there was GH200 previous year. They actually move it a lot to the ARM-based stack, so they like ARM. This is the server, which is like 1U or 2U server, which is basically has 2 GPUs, 1 CPU. In order to manage this 2 GPU, they thought that 1 to 2 is good ratio. And they put a bunch of peripheral, which we will not waste as much time. We will talk a little bit about like networking and BMC, but they put storage, they put some also peripheral devices like CMOS battery and so on. So that's how it looks like. The interesting part about that servers, it has 4 networking capabilities. It's not even networking interfaces, because networking capabilities may have multiple networking interfaces, and each multiple networking interface may have multiple networks. So it's like all of this complex hierarchy, but there's 4 different ways networks should work on these devices. And one way is basically it should work is call it a backend. Backend networking is between the racks. So you have one rack with 72 servers, you have another rack with 72 servers, you want to connect them using this interface. It's called backend networking. Then you have a front-end networking, which is a normal interface, which is basically you may use it just to do normal connectivity, like Ethernet type of connectivity. Then you have BMC, Base Mode Management Controller, which would allow you to manage the server remotely. So that also gives you extra layer of access to the hardware, as well as layer to the attack surface. And then you have NVLink. NVLink is very interesting technology designed by NVIDIA, and it basically makes within the rack the servers talk to each other super fast. So you have connection between the racks, you have connection within the rack, and you have a normal connection. So that's basically kind of 4 different networking interfaces. Each of them need to be configured correctly. Each of them need to be secured correctly. And by the way, each of them implement through multiple different components, which has firmware and custom hardware. So yeah, there's some details on a slide related to like what is names on interfaces and so on and so forth. We'll come back to that maybe later. So there's also the tray way of configuring the server. When you put 2 boards in one server, that's also part of the GB200 configuration. You can do this. It's not as much changes. There you still have a bunch of GPUs, CPUs, they're all interconnected. They connected inside the rack and between the racks. Again, all of this makes a very interesting level of complexity. So when you design all of this, you basically have to build a smart NICs, the smart networking capabilities. That is what BlueField 3 is. The BlueField 3 is a very smart network card. But how smart is this smart network card is? So this network card is smart as the computer. So it's literally like a small server designed as a network card, because it has at least 3 different firmware running on this. It has basically a DPU firmware, which is running on ARM. It has basically data path accelerator firmware, which is running very special NVRISC-V hardware, which is data accelerator, and it has basically its own BMC. And it has a couple more things like adapters. By the way, just an adapter by itself might have a software running on this, which we call firmware, and there's some other capabilities. So if you think about this network card has BMC, which is also a computer. So you have computer on top of computer to manage your network capability on NVIDIA server. Very interesting kind of paradigm in the sense that makes it too complex and makes an attack surface. You can think about different type of attacks from the just networking capabilities, or you can be kind of more like a software type of attacks when you find vulnerabilities. Some of this is based on OpenBMC, which is basically is easy to attack if you know the vulnerabilities in OpenBMC. Some of this is based on Ubuntu, and all of this is running in a single chip, which implements your networking device capabilities. So this networking device could run in multiple different modes, and that's actually not all modes it can run. It also has isolation mode and non-isolation mode. Basically, this network card, if you study that, it's actually as complex as the normal PC. And it basically has very complex configuration, and that configuration is responsible to the security controls, like secure boot, like hardware root of trust, some other networking security capabilities. So that makes these devices quite very interesting attack surface. It has interfaces to manage this device. So something which is called AirShim. AirShim is the way you communicate to this device. And when you communicate to this device, you can basically change configuration, statuses, and so on and so forth. It's basically the management interface of the device, which is basically gives us the next topic is that network card has its own BMC. So the main system, which we call host, has BMC, baseboard management controller, which you use in order to basically manipulate with the server. And then you have network card, which has its own BMC. Theoretically, each BMC should be configured by its own VLAN network. Because if you put multiple BMC in the same network, if one BMC will be compromised, it can basically try to compromise another, which is called lateral movement, and which is basically very dangerous things. You don't want to do it. There was attacks when one BMC took down 200,000 BMCs in one geolocation. So very interesting and important things is how to properly configure BMC and what kind of BMC controls it has. BMC for the network card is basically has the APMI Redfish interface. It has SSH interface when you can get access to, take access to the entire file system and see if you can basically, what you can do in this. So can you basically install a persistent implant? If it's basically Ubuntu-based SSH running ARM server, you probably can do some interesting stuff within the file system or to exploit protection from the file system in order to build some persistency. Let me see. So, 1 second. It was too fast. Almost there. Yes. So that was basically GPU hardware and how does the GPU work. Let me check on time very quickly. Yeah, I have a couple more minutes to finish up. So definitely that gives us a lot of ideas how to build the attack scenario to compromise hardware on NVIDIA stack. Moving on a little bit, a couple more slides about Grok type of architecture. So you probably will just see this slide first right now. You never saw it before. That's on the left side or right side on the picture. You see the instruction set. So it's like 25 instructions. That's pretty much it. The 25 instructions, it's all architecture. It's not like thousands instructions on x86, it's just 25. But some of them given direct access to the memory. What memory is a SSRAM memory, and that memory is like 220 megabytes of memory per chip. Very powerful one. We'll come back in a second on this. But on the left side of this, you see that the stack of implementation. And it's actually going from PyTorch. Some of you who played with AI knows PyTorch. It's basically like a way to implement any AI workload. And then in the end, you see Grok chip. So you have PyTorch going to the Grok chip. All of this level in between make a translation of what you wanted to do from PyTorch on the Grok hardware. So you basically don't know anything of this. You just create the PyTorch like a script, you run it, and it's running on a chip. And you don't know how this level implements and how they protect from each other and which level responsible to make your data integrity in a way that no one compromises it. Which level, who is trusting hardware, who is trusting software, who is trusting who and how. That's a lot of security questions. We still will figure this out. Nowadays, no one cares about this. So basically, you have just a chip, and chip has a memory, and chip has this like instruction set, which give you a direct access to the memory. And if you have direct access to the memory, what you can do, you can actually build the attack scenario when you override the instructions, where the instructions store it, and make some malicious activities. Make an infinite loop, for example, or make a persistency if you will find the storage where to store the thing. Or you may actually generate some things for the future workload. So you sort of create a leftover code within this accelerator in order to compromise the future code of the same accelerator. So that's always possible because the simplicity of the architecture, how the architecture work. And I think I am on time, actually 1 minute over. So AI is not just about model and not just about application, although that's pretty interesting, but it's also a lot about what it is based on, and it has a lot of complexity, a lot of interesting attack surface and vulnerabilities. If you're interested in this topic, just let me know, we can chat more. Thank you very much.
Hello. Okay, thank you so much, Alex. It's very good, actually, AI and hardware. Any questions from anyone? I know you are all excited for lunch, but if you do have any questions, please raise your hand. None? None? If none, there you go. I have one question for you, sir.
A question. Majority of AI models and services are in the cloud right now. So how do you penetrate the hardware when the hardware is in the cloud?
Yeah, it's a super good question. Because the AI require highest performance, it's actually less than on the cloud. In many cases, it's in the cloud in a sense of bare metal access. You can actually renting out the entire hardware. So you're not renting out virtualization level, but you're renting out entire hardware. So all of these models, when you think about private cloud, hybrid cloud, and how to do the highest performance compute, it makes attacker to get the direct access to the hardware. In some cases, yeah, there's a layer of virtualization there, and you basically, that's very depends how would the attacker structure the goal. If the goal will be to compromise, so in most of the risk, it's bringing the hardware if you're doing your own AI workload. So if you're like a big company, you're building your own AI workload and you buy the hardware. That's the risk where the real risk is. When all of these like big companies doing. If you kind of just renting out, you may rent out direct hardware access. It's a little bit more risky because who knows who used that hardware before? Who knows what leftovers with this hardware was before? And there's actually a very rare case when you have virtualization between your AI workload and the hardware. And the interesting part about this virtualization is actually quite shallow, so it's not as big. But even although it's there, you kind of doing the same attacks as you would do for any cloud. So first you need to do escape. Like not you can do like hypervisor escape. It's like an extreme, but you can do just like like escape from the sandboxing capability. So a bunch of companies who is building this AI stack, they're doing this kind of smart sandboxing, which is not as quite smart because it's basically just based on standard Linux sandbox capabilities, and then you basically first find a way to escape that sandbox. But there's nothing different from normally what you would do. The only difference is that AI workload, because it's highly performant, really, really demanding as much as possible to provide the direct hardware access.
Okay. Thank you so much for that. Any last questions from anyone? For relax, let Alex go. None. Okay. So if you have questions, feel free to drop by Eclipsium booth. I know he'll be there. If you have more questions, interested to talk about AI in hardware. So that's it actually for the morning session. I hope you enjoyed. So for